If you could zoom out far enough, past the planets, past Pluto, past the edge of every diagram you've ever seen in a textbook, you'd realize something unsettling. We don't live in a neat little solar system. We live inside a boundary we've never actually seen. And that boundary is so vast, so empty, and so unreachable that it quietly determines the limits of our future. Most of us imagine the solar system as a flat disk, the sun in the center, the planets circling like grooves on a vinyl record, Mercury, Venus, Earth, Mars, the asteroid belt, Jupiter looming large, Saturn's rings, Uranus and Neptune drifting at the edge, maybe Pluto hanging off in the dark. It feels complete, self-contained. But that entire structure, every planet, every moon, every spacecraft we've ever launched, fits inside what is essentially the downtown of our true neighborhood. Because the real edge of the sun's territory doesn't begin at Neptune. It doesn't begin at Pluto. It begins thousands of times farther out, in a region so distant that even light from the sun feels thin and tired by the time it arrives. Astronomers call it the Oort cloud. And if it exists the way our equations say it does, then we are not living on the edge of space. We are living deep inside a hollow sphere. To understand why that matters, you have to forget the shape of the solar system as you know it. The planets orbit in a flat plane, like crumbs scattered across a dinner plate. But the Oort cloud doesn't follow that rule. It doesn't form a ring. It doesn't form a belt. It surrounds the sun in every direction, above, below, and sideways, like a colossal frozen shell. A spherical boundary marking where the sun's gravity barely holds on, and the scale of that shell is almost impossible to internalize. The distance from Earth to the sun, 93 million miles, is one astronomical unit. Neptune orbits at about 30 of those units. That already feels enormous. But the inner edge of the Oort cloud may not even begin until 2,000 to 5,000 astronomical units away, and it could stretch as far as 100,000. That's nearly halfway to the nearest star. If you shrank the solar system so that Earth was 1 inch from the sun, Pluto would sit about 40 inches away. You could place the entire planetary system on a large dining room table. But on that same scale, the Oort cloud wouldn't start until you walked several hundred feet away from that table. Its outer edge would be more than a mile away. Everything we've ever explored is dust at the center of something miles wide. But here's the part that makes this uncomfortable. The Oort cloud isn't just distant. It's fragile. The objects out there, trillions of frozen bodies made of water ice, methane, ammonia, weren't born in deep space. They formed much closer to the sun, in the chaotic early days when the giant planets were still migrating. Back then, Jupiter and Saturn didn't sit politely in stable orbits. They moved. They shifted. And as they did, their gravity flung debris outward like stones from a cosmic slingshot. Some of that debris escaped forever, but some of it didn't move quite fast enough. It drifted outward, slowed, and stalled at the razor's edge of the sun's gravitational control. Over billions of years, passing stars and the tidal pull of the Milky Way stretched that scattered debris into a sphere. Not a wall, not a barrier you could crash into. A barely held together cloud of icy remnants balanced between our star and the galaxy beyond. And this is where the story starts to get uncomfortable. Because objects in the Oort cloud aren't firmly bound to us. They sit in a delicate balance. The sun's grip out there is weak, so weak that the gravity of the Milky Way itself competes with it. The galaxy raises tides in the Oort cloud the way the moon raises tides in Earth's oceans. It stretches the shell. It distorts it. And occasionally, another star passes close enough to shake it. We already know of one. A red dwarf called Gliese. 710 is on a trajectory that will carry it straight through this distant shell in about 1,000,000 years. Not a near miss. A direct pass through the outer boundary of our system. When it does, its gravity will scatter millions of comets. Some will be flung into interstellar space. Others will be knocked inward, toward the inner solar system, toward us. But here's the twist that makes all of this feel almost surreal. We have never seen the Oort cloud. Not once. No telescope has ever captured a confirmed object from that distant sphere. No probe has flown through it. There are no photographs, no direct measurements. The sun's light out there is too faint. The objects are too small, too cold, just a few degrees above absolute zero, radiating almost nothing. So how do we know it's real? The answer doesn't come from images. It comes from comets. In the mid-20th century, astronomers noticed something strange about long-period comets, the ones that take thousands or even millions of years to orbit the sun. They don't arrive along the flat plane of the planets. They come from every direction imaginable. From above the sun's north pole, from below its south pole, from angles that make no sense if their origin were a flat disk. The distribution is random, spherical. That randomness is the fingerprint of a surrounding reservoir. If the solar system is more than 4 billion years old, then the comets we see today shouldn't still exist. They burn away each time they approach the sun. They lose mass. Eventually, they die. The only reason we continue to see fresh ones is because something far away keeps sending replacements inward. A supply tank in deep freeze. The Oort cloud isn't something we observed first and explained later. It's something the math demanded. And that brings us to a spacecraft most people believe has already left all of this behind. In 2012, headlines announced that Voyager 1 had exited the solar system. It crossed the heliopause, the boundary where the solar wind gives way to interstellar space. It was a historic milestone. But here's what those headlines didn't emphasize. Leaving the sun's magnetic bubble is not the same thing as escaping its gravity. Voyager 1 is currently about 160 astronomical units from Earth. That sounds extraordinary. It's traveling at around 38,000 miles per hour. By human standards, it's screaming into the void. By Oort cloud standards, it has barely stepped off the porch. The inner edge of that distant shell lies hundreds, maybe thousands, of astronomical units ahead. Voyager won't reach it for centuries, and by the time it does, its instruments will have been silent for hundreds of years. Its nuclear power source is fading. Within this decade, we expect to lose contact completely. When Voyager finally drifts into the Oort cloud, it will be a dead artifact, a piece of metal moving through darkness, unobserved, unreporting. It may take nearly 30,000 years to cross the entire shell. 30,000! That is longer than recorded human history, multiplied several times over, just to leave our own backyard. And this is the part we don't talk about enough. The Oort cloud isn't dangerous because it's dense. In fact, it's almost completely empty. The average distance between objects out there may be comparable to the distance between Earth and Saturn. You wouldn't see icy rocks floating around you. You would see nothing but stars. The barrier is not what's there. The barrier is what isn't. Inside the planetary region, a spacecraft can theoretically island hop. Earth to Mars. Mars to the asteroid belt. Asteroids to the moons of Jupiter. There are resources. There are pit stops. You don't need to carry everything with you. But beyond Neptune, the islands disappear. There are no refueling, stations spaced conveniently apart, no clusters of rock close enough to matter. If you want to cross the Oort cloud, you must bring every ounce of fuel with you from the start. And the more fuel you bring, the more mass you add. And the more mass you add, the more fuel you need. The rocket equation turns the dream into an exponential wall. With our current technology, a human journey across the Oort cloud would take tens of thousands of years. Not a mission, not an expedition, a geological timescale. Civilizations would rise and fall before the ship emerged on the other side. In that sense, the Oort cloud functions like a natural quarantine, not because it blocks us physically, but because it imposes a distance penalty so severe that it might as well be a wall. It keeps the galaxy out, and it keeps us in. Which forces an uncomfortable perspective shift. We like to imagine ourselves as a species on the brink of becoming interstellar. We talk about colonizing nearby stars, about spreading through the Milky Way. But we haven't even crossed the frozen shoreline of our own system. The Oort cloud is both cradle and cage. It preserves the untouched relics of our solar system's birth, icy time capsules from 4.5 billion years ago, waiting for a civilization advanced enough to reach them. It defines the territory where the sun still reigns. In that sense, it is our inheritance. But it is also a reminder of scale, a reminder that ambition does not cancel physics. Long after cities on Earth have changed beyond recognition, Voyager 1 will still be drifting outward. It will pass silently through trillions of frozen bodies. It will become just another artifact inside the shell, a small metal fossil among the ice. And one day, tens of thousands of years from now, it will finally emerge on the other side. Only then will something built by humans truly leave the solar system. So the next time you picture our cosmic neighborhood, don't imagine a tidy cluster of planets circling a star. Imagine a vast, hollow sphere stretching nearly halfway to the next sun. Imagine everything we have ever built resting deep inside it. And then ask yourself this: if the edge of our own system takes 30,000 years to cross, how ready are we, really, for the galaxy beyond?